Good morning, this is ThA01 Goswami. Today I am going to present our work on data-driven estimation of complex dynamical system using an ecostat network with an ensemble Kalman filter in the loop. The work is motivated by the recent developments in the machine learning techniques to model a dynamical system from input-output data. We propose a sparse estimation approach where we use a neural network to learn the dynamics from the full set observation and then incorporate the noisy, partially observable measurements in the testing or deployment phase with an ensemble Kalman filter. We choose ecostat network, also known as reservoir computer, as our neural engine because it facilitates cheap and fast training. And ecostat network consists of three principal components: the input layer, a neural reservoir with random connection, and an output layer. The adjacency matrix W of the reservoir is generated from a random graph model, and the output weights W out are trained using a least squares optimization approach. An ecostat network trained using the full state measurements can be used to predict the future states in a free running fashion, and the Reservoir Observer, published in 2017, incorporates the partial state measurements by directly feeding it to the ecostat network input. But our proposed method assimilates the partial state measurements through an ensemble Kalman filter using a Bayesian approach, and that also removes its dependence on the initial condition. The proposed method is applied on a synthetic and a real-life data stream. First, the time series data from a chaotic Lorentz 96 model is used to train a set of parallel reservoirs that explores the spatial coupling of the system. In the testing phase, only partial measurements were available. The proposed method outperforms both the free-running ESN and the reservoir observer in terms of L2 error and the correlation coefficient. For a real-life example, it is used to predict the traffic volume on the UMD campus. The training data is supplied from the Numina sensors installed in the 5 different intersections on the campus for 2 months. The method is then tested on the 1 week of data with a different number of sensors visible. It does a good job in predicting the daily variation of the traffic and outperforms the reservoir observer in terms of correlation coefficient. In summary, we have developed a data-driven sparse estimation technique for dynamical system that outperforms the reservoir observer. In future, we would like to explore the controller design using the ecostat network. We sincerely thank Dr. Edward Ott in UMD for his insightful discussions on the reservoir computers. We also thank our funding agencies and the UMD Department of Transportation for sharing the Numina data with us.